Hi everyone, this is Andreas Lenz, and I'm going to talk about the capacity of DNA-based data storage under substitution errors in this talk. So this is joint work with Paul Siegel from University of California in San Diego, Antonia Vartocé from Technical University of Munich, and Eitan Jacobi from Computer Science Department in Technion. So to start with, I want to give a short outline about what the talk is. We will start with a brief definition of the channel model, review related work on this topic, finally give some preliminaries to understand the channel capacity of this channel, and finally give a summary and an outline look to open problems. All right, so why is data storage in DNA interesting? So first of all, it features quite high densities because of the fact that that we store data on a molecular level, which potentially gives an increase of density up to 7 or 8 orders of magnitude over conventional data storage systems. So second of all, what I think is very important, that DNA by itself is never going to be obsolete due to the fact that DNA is the building block of humans, and therefore there's an inherent interest that humans look and understand DNA by itself, which is, for example, not the case for, let's say, floppy disk, which have been used a couple of years ago, but no one uses them anymore. Next, DNA promises to be a long-term data storage method because, as you all know, we can still retrieve DNA from ancient animals, and therefore it promises also to be a medium which is quite long-lived, has long lifetimes. Finally, what I also think is important that as opposed to other storage media, it's quite easily duplicatable, and that in a very massive fashion by means of polymerase chain reactions, which means that in conventional data storage systems, whenever we want to copy the data, we need to build a new hard disk drive, for example, and then copy the data over there. Here we can use just biochemical reactions to multiply and duplicate the data many, many times. All right. Finally, this advantages come with the fact that even though sequencing is still quite expensive, it has dropped significantly over the last few years, which makes the storage system also, from a financial point of view, more interesting. All right, but how does such a storage system look like? So in a storage system, we want to store user data, which is given in binary form. And the first step is to encode this data to some DNA strands, which are here, 3 DNA strands of the same length. Now, once we have encoded this data, we need to physically store the data, which we do by means of DNA synthesis, which means to artificially create these DNA strands in this fashion as we have encoded them, and then store them in an appropriate storage container. Once we want to retrieve the data, we do something called DNA sequencing, which means to read the stored sequences, DNA sequences, and what we get is a collection of sequences here, which we then want to use to decode the original binary data. So there are several aspects that are interesting in the system here. And for one is that, as you see here, there might be errors during the sequencing and synthesis steps, which are highlighted in red here, which need to be coped by our encoding and decoding mechanism in order to avoid data corruption. Second of all, what is also interesting to mention is that we can currently not store very long DNA and also not sequencing it, which means that the length of these DNA strands is limited to roughly 100 to 1,000, and therefore we want to store the data on many, many parallel sequences. And as you see here, we have multiple sequences in parallel. Finally, what's also interesting is that unless we use specifically designed primers for random access, we have no control over which DNA strands we draw here, and therefore we might read some strands none of the times, as for example this purple strands here, or we might read other strands multiple times, as in the case of the blue and the orange strand. All right, but how does the mathematical model of this system look like? So say here we store our input, which are the sequences that we have synthesized, in this case 3 sequences. Now the output is then obtained by randomly drawing from this input and possibly obtaining the sequence with some errors. So in this case, we draw the first output sequence, and which was the original second input sequences, and we obtained some additional errors. And as I mentioned before, this drawing is random, so we have no control over what we are drawing from the input. So we do this a couple of times. In the second draw, we obtain the third sequences, we obtain the third sequence again, then we obtain the second again, and again the third sequence. And each of the times we might receive the sequence with a different number of errors and also in different positions. So while here we highlight the origins of the output sequences with the colors and the arrows, please note that in general, the sequencer does not know which of the sequences he drew. So this association information here is not present to the receiver in a real system, which makes it more complicated, as we will see later. All right, but mathematically, we can then say that each output sequence is just a random draw of an input sequence plus some error vector, where the draws are uniform over the input indices, and the error vectors are have error probability p. All right, in this work, we look at quaternary sequences, which means that we're working over the alphabet of size 4, which corresponds to the 4 DNA bases ACGT. So what are the parameters associated with this channel? So first of all, the input has m input sequences. In this case, we have 3, each of them having the same length L. We can stack these input sequences to a matrix, and which has then m rows and L columns. And we have a parameter associated with this input, which is beta, which captures the logical density of the system, which we will see later is an important parameter for the system. On the output, on the other hand, we have the channel output, which are n sequences. In this case, we have 5 sequences, each of them having the same length. And we stack those sequences to a matrix y1 to yn. And again, we have a parameter associated with the output, which is the coverage. And this is just the number of output sequences divided by the number of input sequences, which is 5/3 here. And it captures the average amount of times we read every input sequence. So note that in this model, we do not incorporate insertion and deletion errors, which are in fact often observed in the DNA storage system. But this is for now left for future work. All right, so how does communication over this channel look like? So say we start with a message of what we want to store. We put this into an encoder, which gives us DNA sequences. Those go through the channel that we just described. Then the output is fed to the decoder, and we obtain the estimate of the original message. All right, so in this communication system, we want to transmit using an error correcting code in order to avoid the errors. And this code is just a subset of all matrices of times m times L, which are the possible channel inputs, because we have m input sequences, each of them having length L, and we view this as a matrix over the alphabet of nucleotides. As usual, we have a code rate, which is the logarithm of the number of code words divided by the total number of channel users, which is just the size of the total number of nucleotides we have synthesized. On the other hand, we have a decoder, which takes a matrix of size n times L, which is here has 5 rows and L columns, and this decoder maps this code to the codebook, and we say we have decoded incorrectly or an error when the decoded result is not equal to the channel input. All right, so this brings us to the notion of channel capacity and achievable rates. And we say, as usual, that the rate is achievable if there exists a code of some rate R, such that the error probability vanishes as the code dimensions tend to infinity. And then the capacity is just the supremum of achievable rate, marking the rate, the largest rate at which we can communicate reliably. All right, so there's some related work on this topic, and I want to start with Mitzenmacher's work, who discusses the multi-draw or binomial channel. And this is just a channel that has multiple, one input sequence and multiple output sequences. And so it has one input sequence and multiple output sequences, and he derived the capacity of this channel. And we will see later that this is an important aspect of this channel. at hand. So second of all, more related to our system, more related to our work is the work by Heckel et al. In 2017, who introduced this channel, however, with no errors, meaning that P equals 0. So they derived the capacity of this channel and showed that it's equal to the simple expression 1 minus e to the minus c and 1 times 1 minus beta. And this has a simple reason why the capacity is given like simple interpretation why the capacity is given like this. And it's as follows. So the first part, the first factor is just the rate that I have to pay in order to deal with sequences that I have never drawn. And the second part is the rate that I have to deal with indexing the sequences due to the loss of ordering of the sequences during the random drawing. All right, so there has been more on this, for example, by Chamoroni et al. In 2019, which discussed a similar channel, however, where each sequence has to be drawn exactly once and with errors. They derived the capacity to be the capacity of the Curie symmetric channel minus beta, which is what we have to pay for indexing the sequences, again, due to the random drawing. More recently, they have generalized this to Bernoulli drawing distribution. So each sequence is drawn according to a Bernoulli distribution with success probability Q. And then the capacity is given as the former capacity multiplied with the factor 1 minus Q, due to the fact that we have to, again, use an erasure correction code for the missing sequences. All right, so in our works, what we did was to find in 2019, we found an upper bound on the capacity of this channel. And in 2020, we could find also an achievable scheme that reaches this upper bound and therefore proving the exact capacity for this channel. More recently, there has been a generalization of our work by Weinberger and Mehrhoff, who generalized this this channel to general asymmetric channels. However, in our work, we only looked at the standard Curie symmetric channel. And they also derived error probabilities for this channel. All right, so let's revisit the channel model and look at it from a slightly different point of view, because this gives some nice intuition about what's happening in this channel. So again, we have here we have 3 sequences stored in the system. And what we say in the first stage, these sequences go through a multi-draw stage, which means that each of these sequences is drawn multiple times and transmitted over a Curie symmetric channel. In this case, as we have seen before, this first sequence has been drawn none at all. The second sequence has been drawn 2 times, and the third sequence has been drawn 3 times. However, this information is not directly accessible to the receiver because the receiver doesn't know the origin of the sequences. And therefore, we model this by a permutation in the second stage, giving the final output of the system. Now, we have shown that this channel model is input-output equivalent to the original model, and it gives some nice intuition about the challenges that arise when we want to communicate over this channel. So first of all, the draws of the multi-draw channels are random because of the fact that also our original draws were random. This means we don't know a priori about how often we draw each of the sequences. Second of all, the second challenge arises in the second stage, which is the permutation of the sequences, which means that we do lose the ordering information of the sequences, and we don't know how to associate the output sequences with the input sequences. All right, so I mentioned before already that Mitzenmacher published an important paper in 2006 about the multi-draw channel, and this channel is simply a channel that takes one input sequence and repeats this output sequence, input sequence d times, and transmitted over a Curie symmetric channel. So we can model the output sequences simply by saying it is an input sequence X plus independent error event EI. All right, the capacity of this channel is computed directly by the fact that we see this is actually nothing else than a discrete memoryless channel with the output alphabet size that is equal to, that has a size of simply 4 to the power of d if we stack each of the the first symbols of each sequence to one symbol, the second symbols of each sequence to one symbol, and so on. And then if it's a discrete memberless channel, we can simply compute it by Shannon's result. And this is what we did in this plot down here, where we get for d equals 1, this is the standard capacity of the Curie symmetric channel, because we only have one draw. Now for 2 draws, it increases, and for 5 draws, it increases also. And we see, of course, these curves are monotonically increasing with the number of draws. And eventually, as we let the number of draws tend to infinity, we approach this dashed line over here, which is simply the rectangular shape that drops down at 0.75. So one thing that I want to highlight here is that already for maybe 5 or 10 draws, so assuming an error probability of 0.1, we see that there's not a big gap between the capacity of 5, 10, or 100 draws, because we already have reached some sort of saturation, which needs to be taken into account actually for efficient system design, which we'll see later. All right, so we have derived the capacity for this channel, and it looks like follows. So first of all, to understand the result, we need to understand what happens to the number of draws of each sequence. So recall that the number of times I have drawn the sequence I is di. And now with our parameters, so we fixed the sequencing depth or the average number of times of draws to be c. Now, because di is simply a binomial distribution with n draws and 1 over m as a success probability, and these di's converge to Poisson distribution. And this motivates why the channel capacity is given as follows. So within an appropriate parameter range, which we'll discuss later, the capacity is given by this weighted sum of the capacity of the multi-draw channel that we have seen in the previous slide, weighted with the Poisson distribution with parameter c and realization d. And this is because the relative number of times we see a sequence being drawn d times is exactly equal to the Poisson distribution as argued above. However, this is only the capacity of the first stage, and the second stage that we have seen before has this random permutation, and there's a rate loss associated with this random permutation, and it's given by this factor over here. All right, so let's discuss the parameter range of this equation. We have seen that it's given by 2 beta being less than 1 minus the entropy of 2b. And if we look at this plot here, the blue region highlights the region where we are actually in the valid parameter range of our capacity result. So this means, for example, that for a beta of 0.05, which is common in current storage system, our capacity result holds until error probability of roughly 0.25, which lies above the usually reported error rates, which means that this result applies for typical parameters that are observed in normal systems. All right, so let's have a look at the capacity expression. So here we just repeat the plot that we have seen before, and now we plot the capacity for different numbers of c. And just as a reminder, c is the number of output sequences divided by the number of input sequences, and therefore, as you increase c, we increase the total number of output sequences. So let's look at the blue plot first, which is for c equals 0.5. We see that we have a capacity that, of course, drops with increasing error probabilities. And as we increase the number of draws, or the c, we see that also the capacity increases. And as we have seen before, at some point, the capacity saturates because it doesn't help to draw any more sequences. And we see, for example, here, when we go look at error probabilities of 0.1, going from 5 to 10 coverage, there is not much difference in capacity. And in fact, as we would let c grow to infinity, we converge to a curve that that is equal to 1 minus beta, so 0.95 in this case, for all values of p, as we will see later. All right, so there are some extreme cases that I want to have a look at. And first of all, as mentioned before, for no errors, we obtained the result from Heckel et al. In 2017, which is given by the multiplication of these terms here. So this is simply when we plug in p equals 0 into this expression above here. Now, As I mentioned before, if we have many draws, this corresponds to letting C grow to infinity. The capacity approaches 1 minus beta. So no matter what the error probability is. And this is explained quite easily because if we have many draws, we can simply cope with all errors by appropriate reconstruction or majority votes on the sequences that we have obtained. And the only thing that we need to deal with is the loss of permutation, which can be dealt with a code that simply indexes each sequence. And this is the rate that we achieve, 1 minus beta, when we do sequence indexing. On the other hand, if we let the sequences grow very long, which corresponds in our model to letting beta go to 0, we obtain a capacity which is given like this. And this is simply the first part of the capacity, which corresponds to the first stage of the channel that we have seen before. And this is because when beta is very small, this means that we can simply index the sequences and protect them with a very strong code without a significant rate loss. And therefore, the permutation of the sequences doesn't play any role anymore. And the second term of this capacity drops. All right. So with this capacity result, we can do something very interesting, which is to look at the trade-off between storage and recovery rates. And to understand this, we first need to define storage and recovery rates. So first of all, the storage rate is the number of bits that I can store per nucleotide that I have synthesized. And on the other hand, recovery rate is the number of bits that I retrieve per nucleotide that I was sequencing. All right, so with these two numbers, we can plot the rate of achievable, the region of achievable storage and recovery rates by the means of our capacity results. And we see that for p equals 0, for no errors, we obtain this blue shaded region over here. And as the number of errors increases, or the error probability, the region becomes smaller and smaller naturally because our capacity drops. However, interestingly, I want to note that even for very high error probabilities, this region has a very flat behavior on the left-hand side of this plot here. And what this means is that even if we drop with recovery rates below, say, 0.2 or 0.1, it's not very efficient from a cost efficiency point of view, because we drop the recovery rates without being able to increase the storage rates anymore. And this means in order to operate cost efficiently, we should rather operate at a point where the recovery rate is still significantly in the not in the flat region over here, but in the more steep regions to have an efficient storage system. All right, so this brings me to the end of this talk, and I want to give a short summary of what we did. So we have seen the capacity of this DNA storage channel under substitution errors. And we have made the connection to multi-draw channels, which was the result by Metzenmacher. And we have seen that this capacity result gives rise to a new cost-efficient design and to understand how we can store data with an optimal or Pareto optimal storage recovery trade-off. All right, so of course this is not the end of the story, because there are many open problems regarding to this channel. And first of all is why this capacity result is theoretically interesting. We don't know yet how to deal efficient codes that operate close to the capacity of this channel. And the problem is that, as I mentioned before, each sequence goes through a channel whose strength is not known a priori. So we don't know how many times we drew each sequence, and compare and disconnected with the fact that we don't know how to protect the indices in an efficient manner. This means that it's still an open problem to design codes that are really close to a capacity. We tried to approach this problem in our 2020 paper, where we modified concatenated codes and obtained codes that operate close to capacity. However, we were not yet we are able to achieve capacity exactly. So next of all, as mentioned before, there are actually errors that we have not talked about yet, and these are insertion and deletion errors over this channel. And of course, it will be interesting to see how the capacity looks like for this channel if we incorporate those. Finally, I also want to mention that in many systems, especially in DNA storage systems, we want to impose some constraints on the input sequences, such as run length constraints and balanced GC content, because of the fact that this gives more stable molecules. And this is something that we have not looked at all until this point. So thank you for your attention. I will be happy to answer any eventual questions.